his PhD. Yeah, so yeah, the next speaker will be Peter Baddoo. Peter completed his PhD in Dant at University of Cambridge, working with Dr. Lorna Ayton. Peter is currently an instructor in applied mathematics at MIT, and he will be talking about the theory of interacting aerofoils. Okay, yeah, Peter, thanks.
Hey, thanks, Elena. And thank you for the introduction, and thanks for taking the initiative, both you and Vikas, in organizing this great conference. I was really excited to see the other speakers and see what they're talking about, because there are so many connections with my work and what other people are talking about. So that's really great. This is a collaborative project between myself, Nick Moore, Nandoza, and Darren Crowdy. And as you can probably tell by the background image, we're interested in fish, in animal locomotion, particularly schooling. And this question of how animals propel themselves through fluid is something that has fascinated both scientists and the public. It becomes a particularly subtle question when we consider the interactions between multiple fish. So not when you just have one fish or bird or whatever on its own, but when you have multiple swimmers interacting. And there are quite a few reasons you might want to study these problems. The first is from just a purely curiosity-driven perspective, because these animals choose to occupy these really intriguing formations that can be quite beautiful. So here we have a ball of fish on the left, and on the right, a murmuration of birds. And it's really interesting to wonder, first of all, why these animals choose to occupy these configurations, and second of all, how do they use hydrodynamic forces to propel themselves into these formations that might be optimal in some sense. But if you're not driven by curiosity, then there are also some more practical reasons why we might be interested in this. The first is that people are now designing robotic swimmers that utilize the hydrodynamic interactions between each other in order to optimize their thrust and their propulsive efficiency. And also energy harvesting is an application that people are looking at. So using some piezoelectric energy generator to harvest energy from a background flow, such as in the ocean. And our motivation for studying this is all of the above, but also there's a new mathematical framework for understanding these problems where you have multiple interacting bodies or agents. And there's a very neat mathematical object that we can use to describe this entire problem. And the main paper that we're basing our work on is this very famous paper by Theodore Wu from Caltech, written in 1960. And he was looking at the swimming of a waving plate. So throughout this talk, I'm going to use the terms plate, aerofoil, wing, fish, bird, all interchangeably. I just mean the object that is swimming or flying in this fluid. And his model was to consider an infinitesimally thin plate embedded in an inviscid fluid. And the idea is that this is a model for fish propulsion. And you can see this example of fish from the Lau lab on the left. And mathematically, the formulation is extremely simple. It's just a two-dimensional potential flow, which means we have a complex velocity, here denoted by W, which is harmonic throughout the flow domain. Now, the flow isn't irrotational everywhere. There is a wake which is shed by this swimmer. So this wake indicates a jump in the tangential velocity either side of this red and blue line. And that adds a significant complication, because now we're not just solving Laplace, we're solving Laplace with mixed boundary conditions. There's one boundary condition on this plate and another on this wake. And Wu's study really kickstarted a lot of other studies into animal locomotion, but also his work connects to classical aerodynamics and particularly thin aerofoil theory, which was the basis for much aerodynamics research in the early part of that discipline. But all these studies were really restricted to a single wing. So unless you're using some asymptotic regime, you can't use these fundamental studies to study interactions between wings. So the aim of this talk and the aim of this study is to develop an analytical mathematical framework to study the interactions between these multiple wings. So the model that we use is identical to that of Wu and identical to those considered by previous authors. Our contribution is that we solve it analytically. And the idea is that you have an assembly of these swimmers that are all executing some types of motions with harmonic frequency, with the same harmonic frequency. So you can see they're all going up and down at the same rate. They could be executing different motions. So this one is heaving, this one is pitching, this one is undulating, and they could have different amplitudes and phases, but they need to all have the same frequency, and they all need to be moving at the same velocity, or equivalently, they're all embedded in a background flow of velocity u. And we assume the fluid to be incompressible and irrotational everywhere except along these wakes that I mentioned previously. And a really important quantity in characterizing this system is the reduced frequency, which is the frequency divided by the background velocity. So in order to attack this problem, we use a number of mathematical modeling techniques. The first is that we just assume small amplitude motions. And there are two reasons for that. The first is that the mathematics will simplify. The second is that large amplitude motions introduce some extra physics, namely flow separation. And that's very difficult to model using this framework. So we're just looking at the small amplitude regime. That allows us to linearize the boundary conditions. So we go from having a no flux condition on a time-dependent boundary to having a time-dependent boundary condition on a flat boundary. So that's indicated here. And you do this for every wing. So here I've just illustrated it with one wing, but you do it for however many wings you're working with. And then it turns out that it's far simpler to work with the pressure field instead of the velocity field, which is W. We work with the pressure field because physically there can be no jump in pressure across the wake, across a part of the fluid. And therefore the pressure can be expressed as a harmonic function that just has a branch cut or a jump in a single slit. So by working with the pressure, we get rid of this wake at the cost of a more difficult boundary condition that we'll see below. So if we do that procedure for all the wings, we end up with this form of problem. We're looking for a harmonic pressure that satisfies some boundary conditions that depend just on these flat slits. So they're time dependent, and their dependence is connected to the types of motions these swimmers are executing. And as is typical in Laplace problems, we introduce a harmonic conjugate so that we're working with a complex analytic function. And as I mentioned, working with the pressure, it simplifies the governing equation, but it complicates the boundary condition. So the boundary condition is the kinematic or no flux condition, namely that the velocity of the fluid on the wing must equal the velocity of the wing itself. So we know V in this boundary condition because that is prescribed by the motion of the wing. V is a function of the wing motion. And then this integral is connecting the velocity to the conjugate of the pressure. So it's pretty disgusting, and you don't really want to apply this boundary condition in practice. But if we hit this boundary condition with the convected derivative operator, then it becomes far simpler. So if we do that, the integral just becomes the imaginary part of the derivative of the pressure. And then the other part just becomes the convected derivative of the velocity. And we've got a minus sign in here as well. Okay, so it seems like a simple problem. We've just got to solve Laplace's equation in this domain subject to these boundary conditions. But analytically speaking, this is a relatively complicated domain. These slits, or these flat lines, could be anywhere. So what would be an appropriate coordinate system to use, and what would appropriate basis functions be, for example? And our solution is to use a conformal mapping approach. So conformal mappings are perfect for Laplace problems because they preserve Laplace. And it allows us to take a problem in a complicated domain, here, which is our physical problem, and then map that to a simple domain, or vice versa. So here we're mapping the simple domain, that is the interior of the circle, to the exterior of this slit. And the hope is that in the circular domain, the problem will become far simpler to solve, and then we can map it back into the physical domain, and that will be the solution to our problem. So this map is very well known. It maps the interior of the circle to the exterior of the slit, and it's called the Jokowski Map. So very simple. And I should mention that our variable in the circular domain is zeta, whereas in the physical domain, it's z. But what we're looking at is the multiply connected version of this map, because we want to map multiple circles onto multiple slits. And actually, it turns out that there's a multiply connected analog of the Jokowski map, which can be written in this form. So this map was derived by Darren Crowdy, I think in 2006, and it's expressed in terms of a transcendental function known as the Schottky Klein prime function. So you can see this map involves this calligraphic k, which is the log derivative of this function omega, and omega is called the prime function, or the Schottky Klein prime function. And I won't talk very much about it today. I think actually Todd is going to talk about it in the next talk. At least he uses it. But basically, every circular domain has an associated prime function, and that prime function captures a lot of the geometrical or topological aspects of the circular domain, such as its connectivity or the positions of these circles. And the great thing about the prime function is that you can phrase many problems, such as this conformal mapping problem, in terms of the prime function, and those expressions are valid for any connectivity. So I can take out another circle on the left, that results in another slit here, and the representation of the map doesn't change at all. It's exactly the same. You can do the same again with a fourth circle, and the map is exactly the same. All that's changing is the prime function. And one of the amazing things about the prime function is that you can do this for any number of circles. So I could take out 1, 2, 3, 4, 400, 400 million circles. Mathematically, the formulation is exactly the same. Okay, so you might think, great, we have a conformal map from a physical domain to a circular domain, or vice versa. Now we just solve the Laplace equation. So it's just a Schwarz problem, or Riemann-Hilbert, or whatever you want to call it. But first, let me show you an example of the map. So this is a doubly connected map going between these two circles. And you'd think, oh, now we just need to solve our problem in our circular domain on the left. By the way, here's the prime function for this geometry. And Q is the radius of this interior circle. But the problem is, if we try and solve this problem, there is actually a singularity on the boundary. So this is similar to what Maria was talking about in the previous talk. We have a square root singularity at the leading edge of these slits. So here I'm showing you the pressure field that is the solution for the full problem for these two plates. I think they're heaving. And if we look at that in the circular domain, we can see that there's actually a simple pole on this boundary. So that means you can't use the classical solutions such as the Poisson or Vallée formula to solve these, because the function is unbounded on the boundary. So we need a way of dealing with that. Here are the singularities. You can barely see the one on the smaller circle, but it is there. So our approach is to remove this singularity, but we remove it in a very special way so that the boundary conditions are modified in as little a way as possible. So our idea is to write the solution, that the complexified pressure field G, in this form. And this first term corresponds to the singularities, the simple poles in the zeta domain. And then the term on the right is what we call the regular solution. So that solution is bounded on the boundaries, well, and everywhere in the domain. So if we want to do this, this function k has to have a simple pole at these points at zeta minus 0 and zeta minus 1. And if you're doing this for a number of circles, a number of swimmers, you just add up all the contributions. So here we would have m+1 swimmers, so you'd sum over this. And the function we choose for k has very special properties. It's very unique. First of all, it has a simple pole, and it takes constant imaginary part on the boundaries. So this k is the same as the function that we use in our conformal map. And it has this very nice property that when the second argument is on the boundary, k takes constant imaginary part on all the boundaries. So that's really nice, because it means when we apply our boundary condition, this number a is just going to vanish, it's going to disappear, and then we can work it out later. So if we go back to our boundary condition, remember it was the imaginary part of the derivative of the pressure, a just disappears because k is taking constant imaginary part. So the derivative is just going to be 0. So these singularities actually vanish from the problem if you write the ansatz in this special way. And then all we need to do is find R. So R is connected to the boundary conditions, and it can be expressed as a Schwarz problem. So it's an analytic function whose real part takes some prescribed values on the boundary. And the solution for that, for multiply connected domains, was found by Crowdy in 2008. It's called the Schwarz problem, which I've indicated here. And amazingly, you can write this solution in terms of the K function again. So you can see K here and also K here. And this calligraphic H, it's just a transformation, a simple transformation of the boundary data. So for H, you plug in the motion of your wing, and then you get a new function. So this is just the motion, and then this function takes into account all of the boundaries. So this solution is all determined except from A. We need to find these coefficients of the simple poles. And to do that, we just apply the original boundary condition, that is the boundary condition without the convective derivative. We apply that on each wing, and that just gives us a system of n+1 equations that we solve for the n+1 constants A. So this is just a small numerical step. It's a very low dimensional system. The dimension is equivalent to the number of wings that you have. So that's the numerical step here. Everything else can be phrased analytically. So let me just go over the full solution again. And here's the procedure. We had our physical problem, and we defined a K function, this calligraphic K, in terms of the Schottky Klein prime function. Then that led us to define a map. And that map was mapping a circular domain to the physical slit domain. And then we extracted the singularities. We could solve a Schwarz problem for the regular solution. And then we found the edge singularities by solving the n+1 linear system. And then that gave us the solution. And the full solution is here. And you can see everything is phrased in terms of K. So that makes analysis of this problem very straightforward, because all you need to understand is K. So we've got K here in the pressure, K here, and also in the map. That's all you need. So we can look at what happens when you have a single wing. In this case, and this is the case that's been studied a lot by other authors. So the K function is just this simple pole, center A with residue minus A. The map, if you plug this in, take beta to be 0, the map becomes the Jokowski map, and then the pressure just becomes this. And this is the famous Poisson formula that solves an analytic function with prescribed real part on the boundary. So that's the solution, and all you need to do to understand this is to understand the K function. And now we're going to look at a few results, so particularly pressure fields and the thrust force on these wings. And I'm only going to present results for the doubly connected case. That is the case with 2 wings. And there are a lot of reasons for that. Part of the reasons are numerical, like this is much easier numerically to implement than more than 2 wings. But also, in a manner of speaking, the interactions between more than 2 wings can be characterized as pairwise interactions between 2 wings. So this is really the fundamental problem that we want to study, and it also connects with some experimental data. So here we're plotting the pressure fields for heaving wings. By the way, heaving, I have some props here. Heaving means that the wing is just going up and down. And we have 3 configurations here, which are inline, tandem, and a staggered configuration. And if they're in phase, they're moving with the same phase. If they're in anti-phase, they're going like this. And you can see some really interesting features of the pressure field, such as some 0 contours connecting the wings and between the wings. In this anti-phase case, this is as if you have a wing above the ground. So this is known as the ground effect problem. And you can see a huge increase in pressure there, which might explain why many animals, such as stingrays, manta rays, choose to operate close to the ground plane, because they can improve their lift and propulsive efficiency there. But the initial motivation for this study was to understand the hydrodynamic role in schooling and flocking. And in particular, how do fliers and swimmers spontaneously occupy formations? And there are some experiments we're going to see on the next slide that we compare to our model. But if you just have one wing, then for it to be in equilibrium, there needs to be a force balance. There can be no acceleration. And the horizontal force balance just means that the drag is equal to the thrust. If you have two or more wings, then there are more conditions. Well, just the same conditions, but doubled. There's one more, because the wings need to be moving at a steady velocity, but also at the same velocity relative to each other. We can't have one catching up or slowing down. So we'd get that each of the wings are in equilibrium if the leader thrust is equal to the leader drag, and the follower thrust is equal to the follower drag. And if we assume that, or if we look at the special case when these wings are executing identical motions, then approximately their drag is going to be the same. And it turns out for them to be in equilibrium, at least a necessary condition is that the leader thrust is equal to the leader thrust is equal to the follower thrust. So this idea was investigated in a few experiments at the Courant Institute, and they've been very influential, one published in PNAS and the other in Physical Review Fluids. And these authors were investigating the formations that these actuated plates occupy if the distance between them is not defined, or the velocity. So they had a rod and they had the plate attached to the rod, and the plate is actuated at a certain frequency with a certain amplitude. And then we just see what formations evolve dynamically. So these, the two wings will hydrodynamically select a velocity, u1 and u2, and a distance, g, such that they are in equilibrium. So we thought we'd apply our theory to this and see how it compares. And we're really thrilled with how well our theory compares with experiment. So the markers on this plot are the experimental data for a bunch of different frequencies. And the color is the difference in thrust between the two wings according to our model. And as I said in the previous slide, but one, the difference in thrust, when that is zero, it is a necessary condition for equilibrium. So it's zero when it's white. So our model is saying along these white contours, the equilibria must exist, or if there is an equilibria, it must be somewhere along this white contour. And amazingly, these markers line up almost perfectly on this white contour in the case for this distance. So this S is called the schooling number. It's basically the distance between the wings scaled by the wavelength. And there's some, we think, incredible agreement with the experiments considering how simple our model is. So you'll see there are some other branches, some other white contours where there are no experimental data. And that's because these are unstable branches. So you wouldn't observe these in experiments, but you would observe these stable branches. And another thing to observe is that as we go further to the right, the agreement with experiments becomes very poor. And that's because there is viscous dissipation of the wake of the leader. And that's not something that's captured by our model. So we wouldn't expect, as you go to the right, for the experiments to still match up well. Another thing we look at is the thrust difference between the wings in different configurations. So those previous results were just for the inline configuration, like this. But we can also look at all different types of configurations. So if we compute the thrust difference for these wings for different positions, we get a plot like this. And you can see there's two distinct regions, a dipole-dominated region, where the behavior of the thrust difference looks like a dipole, and then a wake-dominated region where you have this periodic behavior that is mediated by the wake. And these white contours are the equilibria observed in that PRF paper that I mentioned. But the fact that so those experiments just found one discrete point of this contour, but we've shown that if you move the follower up a little bit, then you can actually get another equilibrium. And these are continua of equilibria. And yeah, you can maybe find a new equilibrium by moving your plate away according to this model. Okay. And we have a bunch more plots for this. This is the difference in thrust, whereas this is the sum in thrust. Again, the ground effect case seems to be a really significant booster of thrust. I'm a bit low on time, so I'll just race through the last few slides. Here we can do a bunch of results for all different frequencies and phase differences. And we also looked at an asymptotic model where the difference between the wings is large. And the idea is that we can reconstruct that wake-dominated region using this asymptotic solution. So this is the asymptotics, this is the exact solution. You can see they're almost identical in the wake-dominated region. And finally, you can also invert these problems into the time domain. So you could look at arbitrary motions. I've just been talking about harmonic motions, but now we could have a wing suddenly pitching up. And this is the effect of that on the lift. And we can also have different heights of wings. So this is connected to the classical Wagner function, which is still used in aerodynamics to this day to think about suddenly actuated wings. So I'll wrap up there. In this work, we've presented this mathematical framework for studying multiple wings operating in an inviscid fluid. And one perspective of our solutions is that these are generalizations of classical thin aerofoil theory, but now valid for an arbitrary number of wings. And the highlight is that perhaps that these results unify experiments, and they also predict possible new equilibria that were not previously observed in experiments. And the aspect I mentioned at the end was the asymptotic and time domain solutions for these wake-dominated interactions. So thanks for listening. I'll be happy to take questions now. But if you want to get in touch, please do email me, and you can see some of my other research on my website. So thank you for listening.
Thank you very much, Peter.